All right, so let's move on here with this idea of adding up an infinite number of terms here. So there is a certain type of series called a geometric series. And the geometric series is nice. They look like this. Okay, so here's some examples. So if you have 1/2 times 3 to the n, this is a geometric series. So one thing to notice about the geometric series is that the n, or the index, is in the exponent. Okay, and so here's another one. Okay, so here there are two examples of geometric series. So you have some number out front, and then you have a number raised to an exponent. So again, notice that n is up in the exponent on that one. Okay, and so there's a really nice proof in the book that uses telescoping series to show that we can find a sum for these geometric series under certain conditions. So we know that these converge when r, the number that's the base of the exponent, is the absolute value of r is less than 1. Oh, sorry. Yeah, 1. Okay. So it's going to converge when r is less than 1. So this one here, if I look at this one, so that 1/2, that's less than 1. So this is going to converge. And here the 3 is greater than 1, so this is going to diverge. And what do we mean by diverge? What we mean there is that it does not add to a finite number. In other words, if I looked at the partial sums, those partial sums would just keep getting bigger and bigger and bigger without any bound. So that would be it would be infinite. Okay, and this converges, that means it is going to add up to a finite number. And for the geometric series, we actually have a way to sum that up, and it's going to be, so it sums to this thing. So you're going to do the first term divided by 1 minus the ratio. So in this case, this series here that converges, well, let's see what the terms of it are. So if n is 1, it's going to be 3 times 1/2. And if n is 2, it's going to be 3 times 1/2 squared, and so on. So the sum of this guy is going to be the first term, that's this term here, 3 times 1/2 over 1 minus the ratio is 1/2. So that's going to be 3/2 divided by 1/2, which is just going to be 3. So if I sum that up, you're going to get the number 3. So those partial sums, if I added up sequence of partial sums, they would get closer and closer to the number 3. So that's a geometric series. They're pretty easy to spot, pretty easy to sum. So you can look for those. There is also this test for divergence. So this is if the limit as n goes to infinity, an is not 0, then the sum diverges. In other words, the only way you can add it up to a finite number is that those numbers have got to be getting smaller. You know, the individual numbers have got to be getting smaller in order for there to even be a chance of it adding to a finite number. If those individual numbers you're adding are getting bigger and bigger, then there's no way that your infinite sum can end up being a finite number. So that's the test for divergence. Now you have to be a little careful here because students tend to try to use that backwards. They tend to try to say, oh, well, the individual numbers I'm adding are getting smaller, getting close to 0, so therefore it must converge, but it doesn't work that way. And the example that you use is this series, 1 over n. This is called the harmonic series. And this series looks like this, so it's, well, I guess it starts at n equal 1, not n equal 0, because what does 1 over 0 mean? Okay, so we get 1 plus 1/2 plus 1/3 plus 1/4, and so on. And what happens with this is this does not converge. So if I keep adding those up, it's going to just increase without any bound. It does not converge, but the limit as n goes to infinity of 1 over n is 0. So this is that counterexample to show that this statement does not go both ways. It only goes that direction. So the harmonic series is your counterexample. So how do we know that the harmonic series does not converge? Well, we prove that using the integral test. So that will not converge, and it will be proved using the integral test. And so I'll show you in just a second what the integral test is. Okay, so when I have a series with positive terms, right? If I have a series of positive terms, I can use this idea of the integral test. So actually, let me start with this. So let me write down the statement of the integral test. So the integral test says this: let well, the book says it this way: let a(n) equal f of n, and so I'm going to write it this way: let f of n equal a(n), where f is a positive decreasing and continuous function. Of x. For some, and it says here for x greater than or equal to 1, but it just has to be that there's some point at which you have a positive decreasing continuous function. And I like to tell my students that this is the fill in the dots. It's like the connect the dots function. So if your function looks like this, so we have 1, 1/2, 1/3, 1/4, and so on. These are your a(n)s. Then your f of n would just be this 1 over x, right? So f of x equals 1 over x, and a(n) is 1 over n. So a(n), that's these dots here. These are your a1, a2, a3, a4, a5, and so on. And your f of x is the function that fills in, that connects the dots. And so since I have that continuous decreasing function, I can integrate that function. And so the integral test says that if the integral from, and it says 1 to infinity, but again, you can start at any point. If your function is not decreasing until 2 or 3 or whatever, you can just start there. F of x dx converges, then this sum converges. And why is that? Well, these two things are going to be related to one another. So if I think about this sum of the a(n)s, well, this height is a1, this height is a2, a3, a4, and so on. So if I summed up these, and each of the widths of these rectangles is 1. So if I summed up these rectangles here, well, and this is why it wants us to start at 1, because because the area under the curve, in this direction is going to be infinite. So anyway, so we can kind of start there. But okay, so say we leave off the first term there and just start at 1. Anyway, so you get this, the tail end of this is going to be made up of, the tail end of this series is going to be made up of these rectangles that lie beneath the curve f of x. So if this f of x converges, and what that means is that it has a finite area under the curve, then these red rectangles are also going to add up to a finite amount of area. So that means this sum is going to also converge. It's going to add up to a finite number. Okay? And it says the same thing opposite. If that integral diverges, then the sum also diverges. And so when we do the integral test, we just need to make sure that we're checking all of these conditions, that we have a positive, decreasing, and continuous function of x. So let's take a look at this infinite sum here. So say I look at 1 over n squared. And so what would the corresponding function be? So we're going to prove, so we will use the integral test. With f of x will be what? Well, I'm just going to replace n with x to make it a continuous function. So 1 over x squared. So I can look at the integral from 1 to infinity of 1 over x squared dx. And so I can integrate that function. I'm going to go ahead and write it as integral from 1 to infinity of x to the minus 2 dx. And then I can just use like the power rule for integration. So it's going to be x to the minus 1, so negative x to the minus 1. And I'm going to evaluate that from, well, so I can't plug in infinity. So what we need to do here is we need to take the limit as r goes to infinity of x to the minus 1 minus x to the minus 1 from 0 to r. So let's go ahead and plug that in. I have minus r to the minus 1. Oh, whoops. My bottom bound is not 0, it's 1. I was like, what? Okay, that kind of freaked me out there for a bit. So minus, and then I have minus 1 to the minus 1. Okay, so what is this? And I still have the limit as r goes to infinity. Okay, so I end up with the limit as r goes to infinity. Okay, so it's going to be minus 1 over r plus 1. And so as r goes to infinity, this bit here goes to 0. And so I'll just be left with 1. Okay, so what does that tell me? That tells me that the area underneath the curve of 1 over x squared, that's this function. It looks a lot like 1 over x, but it's just a little bit, the tail of it is smaller. So this is 1 over x squared. That's telling me that this area from 1 to infinity is a finite number, right? And so if that's the case, then that means by the integral test, that means that, so this thing, n squared, converges. Okay, and I almost forgot, but what I need to do is I need to check that all of these things are true. So is the function 1 over x squared positive? Yes. Is it decreasing? Yes. If you're not sure if the function you have is decreasing or not, you can take the derivative and see if the derivative is negative. So the first derivative should be always negative to make it a decreasing function, and it is continuous. Okay, so so we have all of the things, all of the conditions that we need to be able to use the integral test. So I get that 1 over n squared converges. Okay, so keep that in your mind because we're going to use that in a little bit with the next example.